Okay, welcome back. This is another ALEKS topic. It's called relating vapor pressure to vaporization. This is a good little topic. It's fairly straightforward, but there's a few little things that we want to make sure we're comfortable with. So the first thing that we're going to do is just orient ourselves to this graph. This graph has temperature on this axis and vapor pressure on this axis. So as we increase our temperature, we should expect our vapor pressure to increase. So vapor pressure is the amount of vapor that's coming up off of a liquid. And if we go to a higher temperature, if you just imagine heating up a pot of water, the hotter that water gets, the higher the vapor pressure is. More vapor is coming up off of the liquid. So that's what we're seeing here. And then for our different chemicals, each different chemical is going to sort of have a different trace. And that's really going to be related to the intermolecular forces that are holding these molecules together to one another. And the more intermolecular forces you have, the less vapor pressure you're going to have. It's going to be more stuck together. And then the more vapor pressure you're going to have, that means that the molecules are less stuck together. So you need to sort of be thinking about intermolecular forces, how that relates to this. I think it is definitely a good idea, a good thing to keep in mind. Anyhow, getting into answering these questions, which liquid is the most volatile? So the way to answer this question, or the way to sort of visualize it, is to pick one certain temperature. So let's just pick, I've got a ruler here, pick this temperature of 110. And then as we go up that temperature, that means that the vapor pressure due to orthoxylene is going to be, here about 290-ish, 280-ish, I guess, torr, millimeters of mercury. And then the other chemicals are going to have higher vapor pressures. So the higher the vapor pressure, the more volatile it's going to be. So the most volatile, that's going to be the isobutyl alcohol. And that's just simply because it's the highest up, right? That's all we're looking for. It's the most volatile. It's got the highest vapor pressure. The least volatile is going to be this one at the bottom, orthoxylene. And again, that's just because it's the lowest one, right? It's got the lowest vapor pressure. That means it's the least volatile. Volatile means just, evaporating. What is the normal boiling point of each liquid? So the normal boiling point, that's going to be the boiling point at sea level. So when the vapor pressure is equal to the atmospheric pressure, that's going to be where the boiling point is. So the atmospheric pressure at sea level is 760 millimeters of mercury, or 760 torr. So this temperature here, where these lines intersect with 760 millimeters of mercury, or 760 torr, that's going to be what the normal boiling point is. That's going to be where the vapor pressure is equal to the boiling point, and that's going to be where we see it boil. So for these different chemicals, the first one here, this temperature looks to be about 144. Isobutyl alcohol, that one looks to be about 108. And then octane, that looks to be about 126. I guess it's like right in between, but we'll call it 126. That's going to be our different boiling points. And again, boiling point and vaporization, the relationship there is that when the vapor pressure equals the atmospheric pressure, that's going to be where the boiling point is. So if the vapor pressure equals 1 atmosphere, 760 millimeters of mercury, that's going to be the boiling point, the normal boiling point of that liquid. Okay, last one here. Suppose a beaker of isobutyl alcohol is put inside a sealed tank containing isobutyl alcohol at 105 degrees Celsius. So 105, 1, 2, 3, 4, 5 is right here. And then we're going to be looking for the isobutyl alcohol. So if we bring that up, that's going to be right here. So then at that temperature, our vapor pressure is going to be something like 660 millimeters of mercury, 660 torr. So again, I just took the temperature, 105, up to our line for isobutyl alcohol, and then went over and said that at 105 degrees Celsius, the partial pressure of isobutyl alcohol, we'll just say iso, equals 660-ish torr. So, excuse me. What we want to do then is we want to relate this vapor pressure to the atmospheric pressure inside of that container. So since the vapor pressure is higher, than the atmospheric pressure, that means essentially that this is going to be boiling. This is going to be, this solution is going to be boiling under those conditions. So then after 10 minutes, will there be more liquid in the beaker, less liquid, or the same amount? There should be less liquid because this vapor pressure is a higher value than this atmospheric pressure. If it was switched, right, if these two numbers were switched, if this was a lower number, then we'd actually get condensation happening, condensing back into that liquid, and there would be more. And if these two numbers were essentially the same, then the amount of liquid would be the same. So we're just comparing these two numbers. If this number is bigger, right, if our vapor pressure is bigger, that means that some will evaporate. This should be less. If this number is smaller, then that should be more. If the numbers are the same, then the same. Okay, hope that helps. If that last part was a little confusing, just let me know, and I'll try to clean that up. But this is that ALEKS topic.